Previously, we have seen several rules regarding congruence. In today's video, we will see the last two rules regarding the congruence of two triangles. The first is the SSS congruence rule, which states that when three sides of a triangle are equal to the three sides of another triangle, then the two triangles are congruent. This is called as the side or SSS congruence rule. So the theorem states that if three sides of one triangle are equal to the three sides of another triangle, then the two triangles are congruent. Now, if you look at these two triangles here, this is a triangle with three sides equal to the three sides of the other triangle. For example, this side here is equal to this side. This side, the second side is equal to the second side of the other triangle. The third side of the first triangle is equal to the third side of the second triangle. So both the triangles are matching in all three sides. Therefore, these two triangles will be congruent as per the SSS congruence rule. Now, we want to remember that previously we have seen several different rules like SAS, ASA, AAS, SAA, and so on. But there is no such rule as AAA. Just as we have three sides, we cannot have three angles in a congruence rule. There is no rule of congruence which says there is congruence because three angles are equal. Okay, this is something which we have stated previously in one of the videos as well, that for congruence at least one side has to be equal. So like this here, we have two angles and one side, two angles and one side, two angles and one side. Or we can have one angle and two sides, or we can have all three sides, but at least one side must be equal to guarantee congruence. Otherwise, it is not congruent. Even if two triangles have all three angles equal, we cannot guarantee that the two triangles will be congruent. So this is our first rule, which is the SSS congruence rule. The next congruence rule is applicable to right angle triangles. It is called as the RHS congruence rule, and as I said, it applies only to right angle triangles. Right angle triangle means one of the angles of the triangle is 90 degrees. So we see here one angle is 90 degrees and the other triangle also one of the angles is 90 degrees. So the RHS congruence rule applies only to right angle triangles. So the theorem states that if we have two right angle triangles and the hypotenuse of one side of one triangle is equal to the hypotenuse and one side of the other triangle, then the two triangles will be congruent. So if you look at these two triangles, these are right angle triangles. So we have right angle and a right angle. So there is a right angle, and then the hypotenuse is equal. So hypotenuse here is 5 centimeters. The hypotenuse here is also 5 centimeters. So both the triangles have the same length for the hypotenuse, and another side of both the triangles is equal. So we have the base side here, which is 4 centimeters, and the base side here, which is also 4 centimeters. So we have a right angle, hypotenuse, and a side. Right angle, hypotenuse, and a side which are equal. So we have what is called as the right angle hypotenuse side congruence rule. So based on this, we say that these two triangles are congruent. So if we cut these two triangles, if we draw these two triangles on a paper and cut them, we can place them one on top of the other such that they both cover each other completely. Alright, so this is called as the right angle hypotenuse side or RHS congruence rule, which applies only to right angle triangles. So there is a 90 degrees angle in the triangle, the hypotenuse is of the same length, and one of the sides is of the same length. Here we have the base. We could have the other side also to be the same, in which case the third side will automatically become the same length. Okay, now we have seen these two last congruence rules, which is SSS and RHS congruence rules. Let us now work out an example and apply the SSS and the RHS congruence rules to show some or to find some solution to a given problem. So we are given here in this example a line segment AB. So let's first draw the line segment AB. So we have a line segment AB like this. So we'll mark the ends of the line segment A and B. Then we are given that there are 2 points P and Q on opposite sides of AB. So there is a point P on one side of AB and a point Q on the other side of AB. So that means P and Q are on opposite sides of AB, such that each of them is equidistant from the points A and B. So the point P is placed somewhere here, and the distance of P from A and the distance of P from B is the same. Similarly, we place a point Q on the other side here, on the opposite side. The distance of Q from A and the distance of Q from B is also same. So let's mark these points approximately here. So I'm marking a point P over here and another point Q over here, and then we will join these points with A and B. So let's make a line between let's first mark those points. So the point on the upper side, let's call it P, and the point on the lower side of AB, we'll call it as Q, and we will draw some line segments joining P with A and B and Q also with A and B. So we'll have a line from A to P and also a line from B to P. And the condition that is given to us is that the distance from A and B to the point P is same. So this is what is shown here, such that each of them is equidistant, means same distance from the points A and B. That means the line segment AP and BP are equal. So this line is equal to the length of this line. Similarly, let us join the points Q with A and B. So from A, let me draw that properly. From A, we make a line to Q, and similarly from B, we will make a line to Q. So we have the two lines now, AQ and BQ, and because Q is also equidistant from the points A and B, AQ and BQ will also have the same length. That means AQ length is equal to the length of BQ. So we'll mark them as the two dashed lines here. So AQ is equal to BQ. And what we are asked to show is that the line PQ is the perpendicular bisector of AB. So we are asked to draw a line PQ here. Okay. So the line PQ, which is joining P and Q, we are asked to show that this is the perpendicular bisector of A and B. So we need to prove that. That's right. We need to prove that PQ is perpendicular to AB. That's the first thing. It's perpendicular. And then it says bisector of AB. That means we need to prove that let the point of intersection of PQ with AB, let's call this as a point C. So we'll call this point here as C, which is this point. So we need to also prove, because it's a bisector, it means the line AB is divided into two equal halves by this line PQ. So we need to prove that AC is equal to BC. We need to prove PQ parallel to AB and AC is equal to BC. So these are the two things we need to prove. And what is given to us? We are given that AP is equal to BP. AP equals BP. And we are also given that AQ is equal to BQ. So AQ equals BQ. So with this information, we need to prove that PQ is perpendicular to AB and that AC is equal to BC. Okay. So to prove this, first we need to find some congruent triangles and prove certain angles here. only then we'll be able to proceed. The first thing is, can we look at this picture and determine two triangles which are possibly congruent? This triangle on the left hand side and this triangle on the right hand side, they appear to be congruent. If we fold them on this line, they will cover each other. So we can take the triangles PAQ and PBQ. So let us take triangle. Let's take triangle PAQ and triangle PBQ and see if they are congruent. In these two triangles, okay, we know that AP is equal to BP. That's one side. AP equals BP, that is given to us because P is equidistant from both A and B. And the second side, AQ, is also equal to BQ. AQ equals BQ. Again, how do we know that? Because Q is also equidistant from the points A and B. That is given in the question. And then we have a common side, which is the side PQ. The PQ side is common to both the triangles APQ and BPQ, right? Or PAQ and PBQ. So that's the common side. PQ equals PQ. So we have side, side, side. So by SAS rule, we can say that by side, side rule congruence, by SSS congruence, we can say that triangle PAQ is congruent to triangle PBQ. So these two triangles are congruent. Once we know that these two triangles are congruent, we can apply CPCT. By CPCT, we can say that this angle, which is APQ and BPQ, are equal. So by CPCT, angle APQ equals angle BPQ. So we have APQ equals BPQ. Okay, so we have shown that the two triangles PAQ and PBQ are congruent, and after proving that they are congruent, we have determined some relationship between the angles APQ and BPQ and shown that the two angles are equal. So this angle here is equal to this angle. Okay, this will be useful for us in the next step, because in the next step we will compare these two triangles. This triangle on the left here, the upper left triangle with the upper right triangle. Now we have considered the full triangle on the left and the full triangle on the right. Now we will consider only the upper triangle on the left and the upper triangle on the right and check their congruence. So that means we are going to check for triangles PAC and PBC. Okay, so now in triangles PAC and PBC, so let me write it on the next page. In triangle PAC and triangle PBC, let me copy the figure from the previous page to here also, so that it's easier to follow. Okay, I brought the same figure here on this page as well. So we are going to consider the triangle PAC, the upper left triangle, and the triangle PBC, the upper right triangle, and check for their congruence. So in these two triangles, we have a side is equal. So we know AP is equal to BP. We have already shown that these two angles are equal, and the side PC is a common side. So we will write those three statements. AP equals BP, and then we have angle APC equals angle BPC, because angle APC is nothing but APQ and BPQ. It's the same as APC and BPC, right? So that is what we have shown here previously. So instead of Q, we can write also C because it forms the same angle. So APC is equal to BPC. And then we have the common side, PC is equal to PC. So that's the common side, PC equals PC. So we now have a side, an angle, and a side. So that is SAS congruence. So side, angle, side. So by SAS rule, by SAS, we can now show that triangle PAC is congruent to triangle PBC. So once we have shown that these two triangles, the upper left triangle and the upper right triangle, are congruent to each other, now we can apply CPCT and say a few other things. The first thing we can state by CPCT is that because these two triangles have been shown to be congruent triangles, their sides must be equal. So we can say that AC is equal to BC. So by CPCT, we can say that AC is equal to BC. So that means PQ is bisecting AB. So that is PQ is bisecting AB. Okay, we are supposed to prove that PQ is a perpendicular bisector. We have shown that it is bisector. Now we have to show that it is perpendicular. Again, by CPCT, we can state that by CPCT, because these two triangles are congruent, we can say that the angles ACP and BCP are equal. Angle ACP equals to angle BCP. That means this angle and this angle are equal. Okay, we know that they are equal now, but we still haven't proved that they are 90 degrees. Perpendicular bisector means if it's perpendicular, it means it has to be 90 degrees. So far we know that they are equal. The next thing is, because these two equal angles are adjacent angles next to each other, because it is, if you remember from the lines and angles class, this is like a ray standing on a line. So these two angles, ACP and BCP, are a linear pair of angles. So since angle ACP and angle BCP are linear pair, what happens? Their sum must be equal. So their sum must be equal to 180 degrees. So angle ACP plus angle BCP equals 180 degrees. Now we know that ACP and BCP are equal and their sum is 180 degrees. That means they have to be 90 degrees plus 90 degrees equals 180 degrees. So that means these angles are 90 degrees. So the angle here is actually 90 degrees and the angle here is also 90 degrees. So we have earlier proven that PQ is bisecting AB, and now we have shown that the line PC is perpendicular to the line AB. It makes 90 degrees. So because this angle ACP and BCP is 90 degrees, so combining these two statements, so we'll call this as our statement number 1 and this as our statement number 2. So combining 1 and 2, you can say that from 1 and 2, PQ is the perpendicular bisector of AB. PQ is perpendicular bisector of AB. Okay, so we have used the ideas from SSS rule as well as from the SAS rule, and also some ideas from our previous chapter of lines and angles in proving this particular problem.